तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. So in our series of lectures on basic electronics, learning by doing, we will move on to the next lecture. Before we do that, let us quickly recapitulate what we learned in the previous lecture. In the previous lecture, as you can see on the screen, we discussed the basic characteristics of transistor, especially the output characteristics of a common emitter configuration. We also saw about the basic principles of transistor biasing after looking at the concept of a load line for a given load in a common emitter amplifier. Then we just saw with some examples two different types of biasing schemes. One is called the fixed base biasing, the other is the collector to base biasing. Now in this lecture we will try to look at one other very important biasing scheme, which is called the voltage divider biasing or emitter current biasing. We also perhaps be able to see the basic principle of a simple RC coupled amplifier made use of common emitter configuration of a transistor. So this is what we planned during this lecture, and now you know when I say biasing, you all know by now, I am sure, what we mean by that. We really mean that we want to put the transistor in action at a particular point, which is called the operating point or the Q point, on the output characteristics of a transistor, especially in the common emitter mode. So you can see on the graph a load line drawn on the output characteristics, which is a characteristics between VCE, which is a voltage across the collector emitter junction, collector emitter terminals, and IC is a collector current. So this graph VCE versus IC is called the output characteristics, as you all know, and this is one of the load line that we discussed in the previous lecture. So you can choose different points like point A or point C, D, E or B for as your operating point, and we said this region, which is very close to the y axis, is called the saturation region, and this region which is very close to the x axis is called the cutoff region. And therefore if you want to use an amplifier, a transistor as an amplifier, then you must confine yourself to the active region, which is the region which is generally in between these two. So we must therefore immediately see, we can see that only the point C or D or E can be used, or something in between that can be used as our operating point or Q point. So how do we provide, if I say one point on, let us say the point D, then you see the moment I operate the transistor at the Q point corresponding to point D on the graph, then my collector current should be around 1 milliampere, as you can see on the x axis corresponding to this point D, and I must have the voltage between the collector emitter to be around 10 volts with a power supply which will be operating at 20 volts. The VCC supply is 20 volts and the 10 volts will be the voltage across the collector and the emitter, and 1 milliampere current will be the current through the collector. So this, how do we arrange so that my transistor is at this point, is what we know call as the biasing. So we discussed two different types of biasing. Now we will move on to the next scheme of biasing. This is again one more scheme to recapitulate what we mean by the load line. You can see the VCE is nothing but, the VCE is the voltage between the collector and the emitter, which is nothing but the total voltage, or the VCC minus the voltage drop across the RC. So VCE is nothing but VCC minus IC into RC. By Ohm's law, current into resistance gives me voltage, so IC into RC gives me the voltage drop due to the current IC across the load resistor here RC, and therefore VCE is equal to VCC minus IC RC is the equation to a straight line. And if I draw a graph between VC and IC, this will be a straight line with the intercept at VCC and the maximum current IC being VCE by RC. That is what is shown. VCC is equal to VCC when there is no collector current, IC is equal to 0, and when VCE is equal to 0, IC is the maximum value, VCE by RC. So this is VCE by RC in the graph, and this is VCC. So if I know 2 points, I can easily draw a line, and that line becomes my DC load line. We already saw this in the previous lecture. It is more to recapitulate, and so now I have to, by biasing, I have to put my transistor to operate somewhere along this line, preferably at the middle of the line, so that it may be able to move on either side equally well when I apply a external signal. So let us now move on to the actual emitter current bias. This is one of the very important biasing scheme, and here what we do is, see in this circuit that I have shown, there are two resistors R1 and R2 forming a potential divider, dividing the voltage VCC, so that at the middle point of R1 and R2 I will have a definite voltage which I can use as the voltage to bias my transistor. So the transistor, if you want to bias, you should provide a specific voltage at the base with a specific base current, and you should provide a specific voltage between the collector and the emitter, and you should also make sure that there is a specific current passing through the collector. So that is what we mean, and therefore instead of using a separate battery, we are now trying to generate the voltage required to bias the base by using a simple scheme of potential divider, which we have already seen under Ohm's law and resistances. R1 R2 make a potential divider arrangement, and the midpoint of R1 R2 is the having some definite proportional voltage corresponding to VCC, and that is being applied as the battery for the base. And now the base current will be provided by this voltage, and therefore there will be a base current, and this corresponds to a corresponding collector current and an emitter current. So now what is going to happen is, let us find out what is the voltage VE across the at the emitter junction, and what is the voltage at the collector point, and what is the voltage at the VB. And if I know all the VE, VB, VC and IB, IC and IE, I have made everything ready for the biasing scheme. Now we know what is VE. The most of the application here is a simple concept of Ohm's law. That is what we are going to apply everywhere here. So what is VE? The voltage at the emitter. This is a emitter, and what is the voltage at this point? Voltage at this point between the ground and this point is nothing but the IE. If I know what is the emitter current IE, and if I know the resistance value RE, if I multiply these two, I will get a voltage. Current into resistance is voltage, and that voltage should be equal to VE. That is what is written in this equation here. VE is equal to IE multiplied by RE, that we all know from Ohm's law. And what is VE? You can also look at it in terms of the other voltages. If I know the voltage at the base as VB, and the voltage between the base and the emitter as VBE, we all know for a silicon transistor VBE is about 0.7 volts. So what is VE? VE is also voltage at base minus a small drop across the base emitter junction, which is called VBE, and that is what VE is. So VE is VB minus VBE, and therefore now I can calculate IE. IE now is nothing but VE by RE, and instead of VE I can write VB minus VBE by RE. Usually VBE is very small compared to VB, and therefore we can ignore VBE in some cases, if that is what I have written here. If VB is very large compared to VBE, for a germanium transistor for example, VB is about 0.3 or so, 0.2, 0.3 volts, that is very small compared to VB, which can be about 10 volts, 5 volts and things like that. So in that sense it can be simplified as IE is equal to VB by RE by ignoring the VBE, but this is a more rigorous equation which you can use to calculate what is IE. If you know IE, it becomes very easy for you to know IC, because you know IE is almost equal to IC. The base current in a common emitter configuration is very small component, therefore IE will almost be equal to IB. It is true for all transistors. So what about VB? If you look at the picture now, I said already R1 R2 forms a potential divider, and that only provides the VB voltage at the base. So that is what is done here. VB is approximately or nearly equal to VCC multiplied by the potential divider R2 divided by R1 plus R2. This we have seen earlier in our discussion, because VCC by R1 plus R2 gives the current through the two resistors, multiplied by the R2 gives the voltage across R2 by simple Ohm's law. Therefore VB is nearly equal to VCC into R2 divided by R1 plus R2, and this is the value of the VB. So therefore now what happens to VE? VE is VB minus VB by RE, and now we know VB from the VCC and the resistors that we have, combination that we have used for R1 and R2. So we can get IE, and since IC is almost equal to IE, we also know IC. And what is the voltage across the collector emitter? VCE, that is nothing but VCC minus IE or IC multiplied by RC plus RE. I hope you see the point. Let me quickly go back to the picture. You can see in previous biasing scheme we did not have any RE, emitter resistance, but now we have another resistance in the emitter which is RE, and therefore whatever, if I want what is the voltage across the collector and emitter points of the transistor, you can see the total VCC will be dropped across RC, some will be dropped across RC, some will be between the collector and the emitter, and the other will be across the resistor RE. Therefore if I want this voltage VCE, then I should subtract from VCC the voltage drop across RC and the voltage drop across RE. The voltage drop across RC is ICRC, the voltage drop across RE is IERE. So I must VCC minus ICRC minus IERE will give me the VCE by Kirchhoff's voltage law. But now because IC is almost equal to IE, we are not distinguishing between IE and EC. That is why here we have written VCE is nothing but VCC minus some IC or IE into RC plus RE, because I assume the same current is almost flowing between across both RC and RE. I will find the total resistance RC plus RE multiplied by IE, that is the total voltage dropped across the two resistors. If I subtract it from VCC, what is left will be the voltage between the collector and the emitter. But this is, we have already said it is nearly equal, because we have to make sure certain conditions are certified to make this exactly true. Okay. To rigorously assess the performance of the emitter current bias circuit, it should be drawn as in figure, where what we have done in the other next figure you can see is I have replaced the R1 R2 bias, the voltage divider bias, into the equivalent Thevenin's power supply and Thevenin's resistance. We have seen also the Thevenin's theorem, we did some problems and then assignments with that, and therefore now what is VB and what is VRT we have to look at. Now what is Vt? Vt is nothing but the voltage that is Vb at the base, and therefore it is also equal to Vb, and that is nothing but what we have already written, Vcc into R2 divided by R1 plus R2. So this is the Thevenin's equivalent resistance of the simple R1 R2 network, and that here is the voltage at the base, and therefore Vb is Vcc into R2 by R1 plus R2, which we have already seen. And what is the Thevenin's equivalent resistance? The Thevenin's equivalent resistance, you know, is R1 parallel R2. You should short all the power supply and look at that, and if you short the power supply, R2, the other end of R2 will also come to the ground, therefore R1 and R2 will both be parallel, and the effective resistance of the parallel of the R1 and R2 will be the equivalent Thevenin's resistance. So R Thevenin's is R1 parallel R2, that is what is shown here. This R Thevenin is nothing but R1 parallel R2, and this is nothing but Vcc multiplied by R2 divided by R1 plus R2. Okay. Therefore, the two equations, basic equations of the base side and the emitter side can be written as Vce is equal to IcRc plus Vce plus Re into Ib plus Ic. Now we are ignoring the contribution from Ib. This is a more rigorous equation, and that is why we wrote a simpler equation here for the Vce. Okay, then what about Vb? Voltage at the base is nothing but Ib into Rb, where Rb is actually the Thevenin's resistance Rt plus the Vbe. This is application of Kirchhoff's law. Vbe, which is the voltage between the base and emitter, and the voltage across Re, which is actually combination of Ib plus Ic, or this is equal to Ie. Okay, these things we have already seen. So it is in principle possible that we can look at any divider bias, emitter resistor bias, emitter current bias, and then analyze the circuit completely, because we know what all the different voltages and different currents, how we can get. So maybe we must try to look at an example. That is what we do in the next screen. You want, for example, design an emitter current bias circuit to meet the specification what I have already mentioned. Vcc, for example, is 15 volts. Vce, the voltage between the collector emitter, is 5 volts. We want the voltage here to be 5 volts. The total voltage applied is 15 volts, and the beta DC, the current gain of the common emitter amplifier, is 100, and the collector current should be 5 milliampere. So how do we get that? So you know the Vce should be 5 volts, therefore 15 minus 5 volts is 10 volts, and that 10 volts is the voltage that will be dropped across these two resistors Rc and Re. So this 10 volts is the total voltage drop across Rc and Re. In this case we just take Rc, the voltage across Rc, to be half of the total voltage. That means 10 divided by 2, 5 volts. So we require 5 volts to be dropped here, 5 volts to be dropped here, and 5 volts to be dropped here. That is what it appears. So what is the Rc value then I should choose? Rc will be the total voltage across Rc divided by the collector current, that is 5 volts by 5 milliampere, it is 1 kilo ohm. So we can use 1 kilo ohm for Rc, and then because Ie is almost equal to Ic, Re is Ve by Ic, and that is equal to 5 volts by again 5 milliampere, that is also 1 kilo ohm. So in this bias circuit we will use 1 kilo ohm for Rc, 1 kilo ohm for Ie, and what is Vb? Vb is Ve plus Vbe. We wrote previously Ve is Vb minus Vbe. Now we are writing the other way. Vb is equal to Ve plus Vbe. Ve is 5 volts because we know already, we have just calculated or assumed, plus Vbe is 0.7 volts, assuming that to be a silicon transistor, and the total voltage Vb should be by 5.7. So we want this to be 5.7. That means I must make sure that the R1 and R2 values are chosen, that the value at the base will be 5.7 volts. Then we have designed the biasing circuit according to our initial starting specification. Now in principle we should make the I2, the current flowing through the resistor R2. I will go back to the circuit and show you. The current flowing through the R2 resistor here is called I2. This current should be somewhat about 10 times less than the current Ic or Ie, then only you can make sure that IB is very small. Only when IB is very small I will be able to make use of R1 and R2 itself for finding the potential divider. Otherwise what will happen, this entire combination of the transistor base emitter junction and RE will come in parallel to R2, and therefore you know if I connect resistors in parallel the effective resistance will be smaller than the smallest in the combination, and therefore we should make sure that this combination does not come into significant contribution at this stage. For that we should ensure that the I2 current that is flowing will have to be very large compared to the IB. That means what? The R1 and R2 resistances should be very small in value. But you have another problem in this, and the problem is any amplifier, this becomes later on as an amplifier, if it becomes an amplifier the input impedance or the input resistance, that is the resistance as I look from the input side into the amplifier, should be very large. Why, etc. we will discuss at a later stage, but in principle now let us assume the input resistance in general to a good voltage amplifier should be very high, and therefore that will be ensured only if I choose my R1 R2 values very large. So now here I have a problem. What is that? If I want R1 R2 to decide the base voltage without bringing in the reflected voltage coming from the RE on the transistor emitter side, then I must make R1 and R2 very small so that the current I2 is very large compared to the base current. But if I want an amplifier with a very high input impedance, then my R1 R2 should be chosen very large. So R1 R2 for these two conditions will have to be both small as well as large, which is not possible. Therefore we should try to get a compromise value. The compromise value in general is assumed corresponding to an I2 value which is about 1/10 of the IC value. This is a thumb rule, something like a simple guideline for the design. Therefore I2 approximately should be IC divided by 10. IC we know is 5 milliamperes by 10 gives me 0.5 milliampere or about 500 microamperes. So that should be the value of I2. So now I know I2, therefore I can calculate what is my R2, because I know VB. VB is, we have already found here, 5 volts per 0.7, 5.7. So VB is 5.7 divided by 0.5 microampere, that is the value of I2 that we want, and therefore that comes out approximately to be about 11.4 kilo ohms, which we can correspond to a 12 kilo ohm preferred value resistor available in the lab. So now we have obtained the value of R2. R2 is around 12 kilo ohm. Then the point is how to get R1. It is very simple, because it is again application of Ohm's law. R1 is nothing but the voltage across R1 divided by I2. The voltage across R1 is VCC minus VB, the voltage at the base, and therefore this is 15 volts, VB is 5.7 volts divided by I2, which is again 0.5 milliampere that we have already calculated, and if you plug in the values and calculate, it comes approximately to 18.6 kilo ohm, and therefore we can use some 18 kilo ohm standard value of resistor in the lab. So with this you can see that we have decided what will be the values of the various currents IB, IC, IE, and we have also found what all the different voltages, what all the different resistors R1, R2, RC and RE. Therefore we have completely designed the voltage divider bias with the emitter current biasing. Right. Now I already mentioned to you that IB should be very small compared to I2. So this is a very important condition, when then only the transistor biasing will be stable. The stability of the biasing is a very important consideration. What we mean by the stability? It is basically, stability is with reference to thermal stability. So let us briefly look at the thermal stability. Now you know the transistors are made of semiconductors, and therefore you know semiconductors are very susceptible to temperature variations. So a transistor, therefore even though I make sure that the voltages and currents are very specifically maintained by using different biasing scheme, there is no guarantee that the biasing or the Q point will be a constant point on my output characteristics or on my load line, because if there is a temperature fluctuation, then you would find the Q point also will start moving about the load line. This will certainly happen. So we must make sure what are the factors that will come into the game in bringing about this instability due to temperature. There are two things which normally are very significant. One is VBE, the voltage between the base emitter junction, and the other one is the ICBO, about which I have not told you. ICBO is the collector base reverse saturation current. You know, in all transistor action we mentioned that the base emitter junction should be forward biased, the collector base junction should be reverse biased. So when I reverse bias the collector base junction, there is no forward current going through a reverse biased junction, but there will always be the minority carriers on both sides of the base and the collector, which can cross over without much problem, and therefore they will contribute to a very small but finite current, which is called ICBO, the collector base reverse saturation current. This is a saturation current because at a given temperature this will be a constant. If I increase the temperature, that because of intrinsic conductivity, more bonds and will be broken in the semiconductor, due to which more minority carriers as well as majority carriers will be generated, but the majority carriers are very large in number. The addition due to temperature is very insignificant in the majority carriers, but in the minority carriers this addition due to temperature can be a very significant component, and therefore this increase in ICBO can create problem for us with reference to the biasing scheme. Let us see how. I have shown on the picture here the ICBO, which is the reverse saturation current flowing through the base, and VBE, the voltage between the base and the emitter, are the two important parameters which can produce problems when you do a biasing. The biasing point will have to be a fixed point with reference to temperature, then only my amplifier will behave in the same way I want it to. Okay, the temperature coefficient of VBE, which is actually represented by the small change in the VBE to the small change in temperature delta T. Delta VBE by delta T is called the temperature coefficient, which is approximately minus 1.8 millivolt per degree centigrade for a germanium device, and it is about 2 millivolt for silicon transistors. So you can see for germanium silicon devices the VBE can increase by around or decrease, because minus 2 millivolt for every degree centigrade it can decrease by this amount. It is a very small value for normal considerations, but this can become significant when the temperature difference is very large. For example, in space flight, when a satellite goes into space, the temperature variations can be very large there, and therefore the biasing will have to be very carefully stabilized, otherwise the amplifiers will not perform as well. ICBO, that is what is shown here. For example, here I have shown two forward bias characteristics for two different temperature, one for 25 degrees and another for 60 degrees. You can see it has decreased, the VBE has decreased here, and this will correspond to, for every degree, about 2 millivolts, and that is what is shown here. As a matter of fact, this variation in VBE with reference to temperature for a constant current can be used as a temperature sensor or a transducer or a sensor for a thermometer. So there are germanium and silicon temperature thermometers designed based on this principle, that for a given current IC or flowing through the diode or the transistor, you can have a continuous variation of about 2 millivolts for every degree, and so this, if I can amplify and then read, I will be able to evaluate the temperature. Therefore this can be used as a temperature sensor, which is also one of the applications of that we can think of. Now here we are worried about that variation, therefore we should try to make sure that the variation is not spoiling the performance of any amplifier. The ICBO again approximately doubles every 10 degrees. So it is this value. After 10 degrees you can see it is almost increasing to the same extent. At 25 degrees this is this much, at 35 degrees after 10 degrees it has doubled. So if I go to 45 it will come over here and things like that. Therefore the ICBO keeps on doubling every 10 degrees. This is a much more serious of the two, delta VBE and delta ICBO. The delta ICBO is much more serious. Why is it so? You see, when delta ICBO increases, the IC component will increase, whatever you say. Therefore the effect of change in ICBO due to temperature is to increase the collector current or the emitter current. When the collector current or the emitter current increases, it will also increase the temperature. When the current increases, the I square R, which is a heat dissipation which is generated, that will also increase. So when the temperature increases, the junction temperature, again you will find more ICBO will be generated. More ICBO means larger IC, and larger IC means larger temperature. So you can see each of them helping the other, and therefore it will slowly be a cumulative effect. Due to that you would find the current of the collector, because of the temperature variation, will start increasing without any control on its own, and after some time the current can become very large, and if you are not able to check this, it may ultimately lead to the transistor being spoilt. Due to the large current flowing through that, it will exceed the power rating capability of the transistor, and the transistor may be spoilt. So one has to be very careful. This is what is called thermal runaway. The transistor runs away with larger and larger current due to the initiated by the temperature variation, and the temperature variation increases IC increases temperature. So each one of them help each other and they both run away, and finally we end up with the transistor getting spoiled. So we must make sure the thermal runaway condition is not generated in any amplifier. That is one of the very important things. That is why people say ICBO is much more important parameters to worry about than the VBE. Okay, so the thermal stability of a circuit is normally assessed by deriving a stability factor. Yes, I am not going into the details of the stability factor, but the stability factor is nothing but delta VBE by delta T or delta ICBO by delta T. So one can actually calculate the change or the stability factor for different biasing scheme, and we can try to monitor and control that the transistor does not enter into a thermal runaway condition. Okay, now I am not going into the details of thermal stability as I already mentioned to you, but let me move on with our focused attention to have an amplifier built with the transistor. After biasing, what is it that we have to do? We want to build an amplifier using the transistor. So if you want to build an amplifier, before we build an amplifier, it is not out of place to just understand what we mean by an amplifier. So you can see, what is an amplifier? It is just a magnifier, something which will magnify an input signal into a much larger signal in magnitude. You know, a lens can be used to magnify small objects. In the same way, small electrical signals can be magnified using amplifiers at the output. So I have just shown a block diagram here where the block is actually an amplifier. So if I have a small sinusoidal signal at the input, the output becomes a very large signal. I hope you can see on the screen. So when I have a small input signal which is in the form of a sinusoidal signal applied to the amplifier, at the output you get much larger signal which is an amplified signal. So we must also make sure that it is truthfully reproduced at the output. That means if there is no distortion, this waveform does not involve any distortion during the process of amplification. So this is what we mean by an amplifier. High fidelity amplifier means it is having excellent fidelity, highly truthful with reference to the input waveform. Now there are certain characteristics of the amplifier which also we should understand. Some of the characteristics, for example, is a gain. An amplifier should have reasonably good gain, large gain. What is gain? gain is a amplification factor, which is normally represented by letter A. A is nothing but, if it is a voltage amplifier, for example, A can be V out divided by V in. What is the voltage output that I get? Divided by voltage in. Usually this will be in RMS for an amplifier. So you can see I mentioned that only for an voltage amplifier the gain is V output by V in, because there are other types of amplifiers, for example current amplifier, power amplifier, etc. So in the case of a current amplifier, you can immediately see what will be the gain. The gain factor will be I output divided by I input, that is a current amplifier. Or in the case of a power amplifier, A will be equal to power output divided by power in. So depending upon the configuration, depending upon the type of transistor amplifier, the amplification factor can be voltage or current or power, and you can see it does not have a unit because it is a ratio of either voltages or currents and things like that. So it is a mere number. Usually it should be very large if you want good amplification. The other thing that we worry about in an amplifier briefly is large bandwidth. What do you mean by bandwidth? An amplifier will amplify audio signal. For example, if it is an audio amplifier that we are all familiar with in a public address system and things like that, if I speak at the microphone, I must get through a loudspeaker very loud sound, a magnified amplified signal, but then my speech will not contain one single sine wave because it is composed of several sine waves. The signal will be a complex signal which is a superposition of several sine waves, and therefore my amplifier should be able to faithfully amplify all the different frequencies that are contained in the input signal. For example, if it is a music or an orchestra, you have different types of instruments generating music or signals at different frequencies. All of them should be faithfully magnified and given at the output through the loudspeaker, then only you would get good music coming out of the amplifier. Therefore an amplifier cannot, in principle, amplify all frequencies equally well. There will be few frequencies it will be very well amplifying. There are certain other higher frequencies or lower frequencies you would find the amplifier will not be able to amplify. Therefore bandwidth is one characteristic which helps us to judge how much an amplifier can amplify with reference to frequency range, and that is a very important thing. Usually our audio signals, for example, are from 20 to 20 kilohertz, and therefore up to about 20,000 hertz the amplifier gain should almost remain constant. Then you find the bandwidth is very good for audio amplification. But there are situations where you want to have higher amplification factors for higher frequencies also. They are wideband and several other variations about which we will perhaps discuss little more later on. Apart from these two, the amplifier should also have high input resistance. It is more pertinent to call that as impedance because it can be complex. It will have both real and imaginary parts, and therefore for simplicity I am saying it should have high input resistance, and it should also have low output resistance. High input resistance should be there so that it does not load the input, and low output resistance should be there so that it can drive any load at the output. About these characteristics we will discuss in detail at a later stage, and therefore just I want to mention to you that whenever I want to construct an amplifier I should make sure that a certain basic characteristics are built properly into the amplifier so that it can be made use of very well. Now let us move on to our transistor biasing circuit, which I want to now convert it into an amplifier for amplifying AC signal, alternating signal. So immediately you can see if I want to do that, the circuit that you see on the screen is one such amplifier which is called RC coupled amplifier, common emitter amplifier. You can immediately recognize several of the resistors and the transistor in the configuration because we have just now seen that this is nothing but a voltage divider bias emitter biasing scheme. You have R1, R2 here, you have the RC, you have the RE, and you have the transistor. about which we just now discussed on biasing scheme. So if I want this to become an amplifier, I have a signal here, input signal, which can be from a microphone or from any standard signal generator. I have to couple it to this amplifier. This is at the Q point. It is now positioned at the Q point along the load line. Now I want to give a signal here, and that signal I want to couple to the base. For that I use a capacitor here. Why do I use a capacitor? Because I want to only couple the alternating component, and if this by chance, if this input signal contains some DC, I do not want the DC to come here. If the DC comes, the base current which I maintained constant previously by biasing will get altered. That means my Q point will shift. I do not want that to happen, and therefore I use a capacitor here at the input to isolate the DC, or the biasing will not be hampered by this capacitor. Therefore this I use, this is called the coupling capacitor, because it is coupling the input signal to the base of the transistor. And similarly I use another coupling capacitor at the collector for the output, with which I can couple to any external load RL that I have connected here. So this is a coupling capacitor at the collector terminal, and this is the coupling capacitor at the input terminal at the base, and these two are the additional things that you see here. These two are meant to couple a signal at the input and couple the output signal to the load. Apart from that, you also see there is another capacitor here. This capacitor is called bypass capacitor. This bypass capacitor also is meant to maintain the Q point constant, because you know this VE, the voltage at the E at the emitter junction, emitter point, should be constant if I want the biasing to be constant. But when I amplify the signal, the collector current or the emitter current can vary, and therefore there will be a alternating voltage according to the signal here, and that means the bias point will also start shifting along the load line. That should not happen. Therefore if I use a bypass capacitor, all the alternating current component will flow through the lower resistance path provided by the capacitance. You know, capacitance offers less resistance to alternating current, more resistance to DC. We all know that 1 by omega c, where omega is the 2 pi f, the frequency component, and therefore higher the frequency, the lower is the resistance offered by the capacitance, and therefore you would find all the resistance, all the signal, AC signal will find a easy resistance path compared to RE, and they will go back, and that means this voltage VE will not be modified by the signal that I am amplifying. So this is a bypass capacitor. These two are called coupling capacitors, and the choice of these capacitors will have to be carefully made. We must know what is the lowest frequency that we want to amplify, and at that lowest frequency this should offer very low resistance. So if we go to higher frequencies, automatically the resistance offered by the coupling capacitor will be less, because it is 1 by omega c, I already mentioned to you, and therefore you would find the proper choice of capacitors is essential to make the bandwidth very good, the frequency range for which this will amplify very good. So with this, now you can see, if I now put a capacitor, apply an input signal, I should get an output signal. What is actually going to happen is, if I apply a sinusoidal signal at the base, that will be coupled here. You can see that immediately comes over here, and that means the base voltage is going to oscillate according to the signal, and because of this the base current will also going to oscillate according to this. When the base current changes, the collector current also will change, you know that, and because of that you would find when there is a larger base current, there will be larger collector current. A larger collector current will produce larger voltage drop here, and therefore when the voltage here at the base increases, the voltage here at the collector decreases, because there is an inverse proportion here. This increase in current increases the current, and this voltage is your constant voltage minus your voltage across RC, and because this is increasing, the voltage here will have to decrease, and therefore you can see this voltage at the collector will be inverted or 180 degrees out of phase with reference to the input signal that I give here. This is a very important idea that we should remember. There is a phase inversion. Okay, now this is what, this will be naturally amplified, because the variation here is in microamperes, the variation here in milliamperes, that means there is a gain of nearly 100 or so, and that will come out here, and when it is applied to a large resistor you can get a very large voltage here. That means this acts as a voltage amplifier. So this is a very simple scheme. I have drawn all the graphs here with this is voltage B, VB at the Q point. You can see it is shifting slowly in a sinusoidal fashion. Similarly the V out also is sinusoidal. The difference is this is even though they look alike, this is very small, this will be very large. And similarly here this is the VE also will show this, but the biasing will not recognize this because it will be bypassed through the capacitor, and but the VCC, the voltage, will be always constant because we are not changing that, that is from a regulated power supply. And so I have shown here with the load line, if this is the biasing point, if I have a signal, for example if I have a signal like this, that means what, the signal is having corresponding to IB is equal to 20 microampere and it goes up to, let us say IB is equal to 40 microamperes, that means it is changing IB by nearly 20 microamperes. Similarly on the downside it can go up to this point, that means there is a 20. So this input sine wave is producing a 20 microampere plus or minus variation in the base current, and that will correspond to a corresponding change in the collector current here. You can see that, and that will correspond to a corresponding collector emitter variation here. So that is why you get a very large signal here. This is a large signal which is corresponding to the output, and if I shift the operating point to some point here, you would find I will not be able to have perfect reproduction here in the sine wave. If I give large signal which is varying by 20 microamperes, the 20 microampere you get only 10 microampere is available. Beyond that if I go, you would find there won't be any signal, therefore the signal will get distorted. So that is the reason why I say I must always bias on the load line nearly at the middle point, midpoint of the load line, then I will have equal excursion possible on both sides of the load line, and therefore I will get reasonably good amplifier. Okay, I have taken a simple example where I have put 33 kilo ohm, 6.8 kilo ohm and 3.3 kilo ohm as the load and 1 kilo ohm as the RE, and with this we will just try to see whether there is an amplification. We will quickly go through a simulation experiment. So you can see there is a breadboard here and you have the transistor BC107, you have R1 33K and R2 6.8K, and this is the RC which is 3.3K, and you have RE 1 kilo ohm, and you have the coupling capacitor here, and you have another coupling capacitor here at the collector, and this is the load resistor which is about 10 kilo ohm here, and this is a bypass capacitor that you see. So it is exactly same as the circuit that is drawn here, which is also the circuit which you saw previously. And now let me quickly switch on the oscilloscope. Immediately you can see I have a 10 volt VCC and I give about 2 millivolts AC source at about 1 kilohertz frequency, and you can see the input signal is very small, the output signal is very large, amplified signal you get. So it is very easy to construct a simple RC coupled amplifier making use of a simple transistor and a voltage divider bias or whatever. In this case I have given an example using the voltage divider bias. Now what I will do is I will quickly show you an actual demonstration with the breadboard, a similar circuit constructed on the breadboard, and we will try to see whether we are able to see an amplification of the required number. I have on the breadboard here the same circuit which I just now showed to you. For example, you have a 3.3K RC, a transistor which is a BC107, this is a 1K resistor, this is a 30 kilo ohm resistor, R1, R2 is 6.3K. So this forms the voltage divider bias that we already discussed. RC, RE, transistor, R1, R2, this forms the voltage divider bias. I have put a coupling capacitor and a AC signal source. This is the AC signal source which is a function generator which can generate different types of waveforms, sine, square, triangle. I have chosen the sine wave, and these are for selecting the frequency, these are for varying the frequency and the amplitude. I have kept the around 1 kilohertz frequency and I have kept at some small voltage few millivolt. Now this input is given at this point corresponding to this input, right, at the capacitor, and I have a power supply VCC which is again about 10 volts, 9.8 volts that is being applied here, and the output I am applying to an oscilloscope. This is the oscilloscope. I have two channels, channel 1 and channel 2. I connect the channel 1 to the input side and connect the channel 2 to the output side, and therefore I have in the two channels, this will be the input, this will be the output. Right now I have not switched on, so you are not able to see the signal. So this is the oscilloscope which I can use to find what is the output signal and the input signal simultaneously. This is a function generator which I am using as a signal source and applying the signal to the input of the amplifier. This is a power supply which I am using for the VCC supply that I require for my transistor amplifier. Now let me quickly apply the AC volts at the input, and so you can see both the signals are seen. Okay, this small amplitude is the input signal. This is the input signal. So if I, for example, if I remove the signal, you will see the output will go blank, straight. Input also will go straight. Now, so this is the input signal. This is the output signal. If I remove it, the output will go flat. There are only noise signals. So when I connect the output, I get an amplified signal. How do I know it is amplification? There is amplification. For that you should see there are amplifiers here in the oscilloscope which is maintained at different points. For example, so this is corresponding to the highest magnification, that will correspond about 5 millivolt. This is around 10 millivolt, and this is about 20 millivolt. So you can see my input signal is within one division. My input signal is at one division peak to peak. That means it is about 10 millivolts is the input signal that I am applying. The output signal is the amplified version. So this if I increase the input signal, the output signal also increases, but there is also a distortion here. You can see it is not an exact sine wave. Now what I will do is I will change one of the resistor with a potentiometer and then try to see what happens. That is, I am removing the RE, I am removing the emitter resistance and replacing it with a potentiometer. It is a 10 kilo ohm potentiometer. So if I now vary the potentiometer after connecting the power supply, if I vary the, so now you can see a highly distorted output. So if I now decrease or increase, you can see the distortion will increase or decrease. So one can choose without distortion by changing this. So you can see when I do that, I am able to reduce the distortion. If I increase it, you will see the distortion increases, right. So I just want to indicate to you that the choice of the various resistor, especially that Re, which is the biasing resistor, is very important in choosing the performance of the amplifier. So you do get amplification gain, even though it is not we have not actually calculated what should be the gain in this case, but we do get enough amplification. So you can see the biasing circuit is very important. After that you have to use coupling capacitors, and this is the bypass capacitor. Once you do that, what you get is a RC coupled amplifier of a one single stage. Now if you want larger amplification, you can actually go for one more of this and couple this to the base of the next amplifier, and still you can have further amplification. So one can actually cascade different amplifiers and get very large gains by having multi-stage amplifiers. So we will see the actual some of the basic theory and the models behind the transistors, and then about the construction of multi-stage amplifiers, etc., in the next lecture. So we will in the next lecture we will try to see how to model a transistor, and then how it can be one can design a basic simple amplifier using that model and obtain the amplification factor and etc., other factors. Thank you.